to another exciting computer architecture class. We've got a homework that's due. I think it's homework number 9. I saw a number of attempts already. Let's see if we can bring that up. Yeah, datagram programming. Were there any questions about this homework? I believe it is due the 5th. No. Yeah. Due this Thursday evening, which is, I'm looking it up now, the 12th, I think. Isn't that right? Yeah. It's due Thursday the 12th. Any questions? And end of day, Thursday. No questions about datagram programming? So somebody had asked me, is the computer networks course cross-listed at the graduate level? Yes, I believe it is. And if it's not, it should be. And someone else said, well, what if I'm in the 5-year program? Blah, blah, blah. I said, please take the course because we need the enrollment. So yeah, we'll do a real live network programming course. And we'll do it using remote learning. That means we will be unfettered by campus networks because we'll have our own networks at home. And that means we can do what we want. No reason for anybody to feel like we're violating somebody's security. So that's a fun course. And I think computer scientists can take it as an elective, but they got to get permission from their advisors. Probably electrical engineers could take it if they wanted. Don't see any mechanical engineers taking that course. Computer engineers used to take it, and are certainly the ECE master's students would want to take a course like that. Reasonable course to take. Our next homework is going to be about distributed computing, and I wanted to cover a network bus. Network bus. So is it a network or is it a bus? And the answer is yes, it is. So when we think about, let's say USB, Universal Serial B stands for bus. Although I suppose you could make it stand for whatever you like. You could have USB for Universal Serial Beer, the beer bus. Anyway, there's this idea that, you know, if it's a bus, it's not a network. And if it's a network, it's not a bus, unless it's a network bus or a bus network in like the USB. And in a bus network, we have an interesting topology. That's the topology that you would get when you hook up the various hubs of the network bus together and then chain them. So lest you think it really isn't a network, there is networking going on. So let's have a look. What does it mean? Well, let's see. About this Mac. We're sitting here. I'm using a Mac. I can get a system report on the Mac, and it has a USB bus, a bus network, in fact. And first thing we see is a hub. And then that hub has another hub. So there's that internetworking going on. Excuse me. Then there's another bus coming in with another hub, more hubs. So the hubs are hooked to the hubs, which are hooked to the hubs. And it's just a ton of sort of hubs, I guess. And so there's even a bridge. Here's a bridge that goes to it from one bus to another bus. This is the Apple desktop bus, which lets me use old style keyboards. And there's a USB converter so you can convert from one bus to the other bus. Bus bridge, the bus bridge. There's USB receivers. Oh, geez. And then there's can't stop it. And then there's another USB hub with more USB stuff, like the microphone I'm talking to, a USB serial port, and there's Let me see if I can turn down this silliness going on with the phones. And then here's another USB hub. And finally, there's some hard drives and hubs that go faster than other hubs like USB 3. So it truly is a network. And it's a network of USB devices, really. Each one of the hubs is another USB appliance. So we've got an opportunity here now to examine a microcontroller's version of one of these USB buses. And I got to turn off this phone. It keeps buzzing at me. And so what we'll do is take a look. Let's do a deep dive. Deep dive into the buses. So this I2c bus is a bus network, just like USB. It has the so-called network topology, which we just looked at, in which nodes are directly connected to this common half-duplex link. It's half-duplex because you can't communicate in two directions at the same time. You have to stop and wait for the bus to be finished being used. And then other nodes can have a chance to take a turn, and then they can talk. So what happens when two nodes try to communicate with the bus at the same time? Anybody have an idea about that? Let's see. We're going to call on people here. Stephanie. I'm going from the bottom now to the top. Stephanie, what happens when two nodes talk at the same time on the same wire?
There would be kind of a miscommunication. We wouldn't be able to understand what each node was saying.
That's correct. That's exactly right. It's what they call a collision. So in Ethernet, what you get is carrier sense multiple access with collision detection. So when something is trying to communicate, the carrier is already present, so the node will wait. But if two nodes do try to communicate at the same time, that collision detection causes a wait for retransmission by an algorithmic amount. So we'll say the node number times some epsilon of time. So if I know my node is 10, I wait like 12 milliseconds, whereas somebody else's node might be 14. They might wait 14 plus 2 or 16 milliseconds. So as a result, we wouldn't collide a second time the next time we try to retransmit. I2c buses are interesting. They're relatively inexpensive, and they are a way for manufacturers of integrated circuits to generate a protocol for the integrated circuits to talk to one another and to talk to relatively simple devices like 8-bit microcontrollers. And so that's an interesting idea, because if your circuit if your little, we'll say, integrated circuit can communicate with somebody else's little integrated circuit, then you can essentially add value to the network bus, right? So one person's I2c device could be an A to D converter, another one could be a DAC, a third one could be like a little memory, a fourth one could be some double EEPROM, a fifth one might be like an 8-bit toaster controller that tries to coordinate all the other devices. You could even have two 8-bit toaster controllers talking to one another on the I2c bus. And it's a 2-wire bus, so that's convenient. But because it only has one data line and one clock line, you pretty much have to say that there's just one source of the clock, which kind of makes it the master. And the data line has to be shared by all the other nodes on the network. So just like Ethernet, it's a broadcast topology network, which means carrier sense multiple access with collision detection, CSMA-CD. And any node can connect to any other node in the network, And if one node is slower than the other nodes, you really have to run the network so that it can accommodate the slowest node. So what'll happen if you have, you know, something like a router on your network that can do a gigabit per second, and you hook it to an ether switch that can only do 100 megabits per second, well, that's going to act as a bottleneck. And that network is not going to work properly at a gigabit per second because it just can't. It's got to run no faster than the slowest element on the network. Data transfers between ICs and systems are relatively low, up to 3.4 megabits per second, which, you know, that might be fast enough for some applications, maybe a lot of applications. If all you want to do is transmit the temperature with the time, yeah, go for it. This is a nice, slow bus, very inexpensive to implement, can go very long distances. And you've got a lot of ICs that speak in this bus protocol. And this is a very popular bus. So there are a couple of problems when you have a bus. One of the problems is electrical. A long wire acts like a transmission line. It's going to have parasitic capacitance, which means that for every foot of twisted pair, you might have 11 picofarads of parasitic capacitance per foot. And so that acts like a big low-pass filter. Even worse, when the square wave hits the end of the bus, it could reflect back. And if it reflects back, that could confuse the other devices. So think of it a different way. Think of it like going into an auditorium. Nobody's seated there. There is no dampening on the walls. And you shout into the auditorium, and what happens is you hear an echo back. Well, you know it's your voice, but the electronics doesn't. And so what happens when you hear that echo back is you think, well, for me to defeat the echo, I either have to put people in the seats because they will absorb the sound, or I have to put in sound deadening materials on the ceiling and on the walls, and that will absorb the sound. So what you do with a bus, an electrical bus, is you provide what's called a termination point, usually at the end of the bus. And in that termination point, you might put in termination resistor. So now if you have, you know, essentially a very long wire, which acts as a capacitor and a resistor, you've got a little low pass filter, and that dampens out the square wave and doesn't come reflecting back and confusing everybody who's listening to the serial clock line and the serial data line. Because if you double up on the data with echoes and double up on the clock with echoes, that just confuses everyone who's listening to the bus because they don't know who's originating the signal. And so then you get a bunch of negative acknowledgments coming through because everyone got confused. It's like two people talking on the radio at the same time. It's no good. So if you have to think about it as a transmission line, you have to think about terminating the bus properly, which means figuring out what the capacitance is and what the resistors should look like at the termination point at the end of the bus. Moreover, if one of the lines on the bus gets severed, everybody down the line is going to be isolated, and that's a problem. So you have a single point of failure. But assuming the wire doesn't get cut and you've terminated it properly, it can be a perfectly reliable way to do data transfer. You can have one CPU take over from the other. So this is what they call multi-master capability. You can have, you know, there has to be a master at any one given point in time, but it doesn't have to be a fixed master. So you can trade off who gets to be the master of the bus. Classic issues here, 400 picofarads of parasitic capacitance for 12 feet. That's a lot of capacitance right there. And lots of different ICs available. This started with a standard that came out of Philips Labs, and it was adopted as a de facto industry standard. I mean, there's thousands of chips that use this bus, thousands of chips. So let's see. The master has to initiate the transfer, generating start and stop conditions. It has to generate a clock, transmits an address. Okay, so if you've got a bus with only 2 wires, the only way to identify the device you're interested in is by its address, which means every device on the network must have a unique address. Or else, 2 devices could respond in the affirmative when you ask the device if it's alive. You've got 2 different devices saying, yeah, we're alive. That's not good. Then there's a collision. So we want to make sure every slave responds only when it's addressed. Whoops, went the wrong way. So here's the I2c bus configuration. And you can kind of see why this kind of looks like a network, right? I mean, this has that network look and feel, but it truly is a bus. We'll call it a bus network, I suppose. And you can just add all kinds of interesting things. 2 microcontrollers, LCD driver, double EEPROM, AD converter. Here's a gate array. And you have serial data, and you have serial clock. The funniest thing, I saw a card, an electronic card that plays some music, and I took it apart. It had an SDA line right on it. It was a little microcomputer. It looked like it had an I2c bus, all built into the printed circuit board. And in fact, I haven't tried to decode it, but I could. I could plug it into my Arduino and see what the card looks like from a protocol point of view. Great fun hacking into greeting cards. And there's nothing wrong with doing that. I mean, that's all very educational, isn't it? So there's a compelling argument. There's a little electrical engineering going on, maybe a little bit more than we might be comfortable with going through just a simple computer architecture class, but it is part of a computer architecture. And just because it's for small computers and small chips makes it no less important as an architecture. And so we should be aware of these things. USB is a bus. It creates a bus network, which is also an architecture, and this is very similar to that. So here's what you get when you have a bus. You get everybody hanging off the same wires, but they have to go to a high impedance state when they are not selected. So I don't want device 1 weighing down on the bus if it's not being addressed. And that's a key. I would like every device to go to a high impedance state when it's essentially not the chosen device for communication. R sub P stands for pull-up resistors. And what that means is that when we assert to ground, this will create essentially current to ground, which is equal to E equals IR. So it would be E over R, which would be VDD over this resistance, the pull-up resistance. And so you have to make sure that resistance is high enough so that the current doesn't, I don't know, draw, so you don't draw too much current, put it that way. And here's an interesting idea. We want to be able to sample on a specific point in the clock. So you can have a sample on a rising clock edge. And then when there's a falling clock edge, you can allow the data on the data bus to change. But when the clock edge is on the rise, you'd like the data to remain stable during that entire sample period. Hold on just a second. Sorry, I had to take off my sweater. I was getting burning up. So let's look at this timing diagram. I know that's a little bit more detailed than you would normally get in an architecture class, but people have to think about these things when they start to put the computers together. So the bus has to have a busy state, and it has to have a state where data can be guaranteed to be valid. And if we want the data to be sampled during the rising clock edge, it has to be held stable during that period of time, or else we've got a problem. Then there's more, right? When data is being transferred, we have to secure the data, make sure it's not corrupted. And one way we can do that is with a checksum. And a checksum, I don't know how much you guys are familiar with checksums. Have you heard of checksums, or do people know about checksums? Let's see.
Professor, is a checksum like a value that is expected from the data, like the size or the expected like hash value per se?
That's exactly right. So you can formulate a checksum by using various operations, such as an exclusive OR operation. So suppose I said it's 10001. If I do the exclusive OR, then I have one exclusive OR with 0, exclusive OR with 1, exclusive OR with 1, exclusive OR with 0, and that gives me a checksum. I don't know why this little thing is here. 10110, right? So 1 exclusive OR with 0 is 1, exclusive OR with 1 is 0, exclusive OR with 1 is 1, exclusive OR with 0 is still 1, so I would get 1 as an output. That would be considered a parity bit. And what it does, because it gives me 1, 2, 3, 4, or an even number of ones, this would be even parity. So an even number of ones means even parity. So we can create a little parity bit just by using a series of exclusive OR operations. And then that is a way in which we can check to see if an error has occurred. This is known as BEC, for backward error correction. It's backward error correction because it goes back to the transmitter and says, I have obtained a bit vector, which is an error because the parity didn't work. And so because of this parity or checksum error, I'm doing an automatic retransmission request, or ARQ, automatic retransmission request. I have to go back to the transmitter and say, send it again. This came out with an error, and I have detected that error. And so classically, we call this an error detection code. Error detection codes are critical for reliable, low-level data communications. This is the Father Marconi School of Communication Systems, where you learn everything you need to know about communication systems, a 15-week course in 15 minutes. Ready, set, go. And so then you have another kind of error correction known as forward error correction. This is forward error correction. And this is a forward error correction because you can't go back to the sender. There's no automatic retransmission request, right? You must take whatever the code is that came in and figure out what went wrong and fix it. Fix it on receipt. So how do you do that? And the answer is you impose redundancy. So redundancy means an error correcting code, which is quite different from the error detecting code. So an error correcting code essentially allows you to take the code word and determine what bits have flipped. And in doing so, you can flip the bits back and fix the code word so that you can recover the data. And the applications for that could be a deep space network, DSN, where you have, for example, Voyager, which is outside of the heliosphere of the sun, transmitting back to Earth, where there are satellite dishes dotted around the planet listening to Voyager, and you can't send anything back because it's not listening. It doesn't have the ability, because it doesn't have the same kind of network, that same kind of satellite dish network to be able to receive. So it's an output-only device at this point. Similarly, if you have a CD-ROM, you can go back and try and reread an area of the CD-ROM, but if it's got chicken schmaltz on it, you're not going to be able to get through the grease. And so you've got to be able to recover the data or simply declare the data as lost. If there's a magnetic tape and the oxide is flaked off the tape, you may not be able to recover that data. So if you have some sort of error correcting code, that will facilitate data recovery. So forward error correcting codes typically have reduced utilization. Utilization, U, is equal to the amount of data that you're attempting to transmit, that's the payload, divided by the overhead in the header, plus the actual data. So if we think about it, if we have one start bit, one stop bit, and no parity bit, we have to spend at least 2 bits for every byte that we send using RS-232. So in the code 8, none, 1, 8 data bits, no parity, 1 stop bit, 1 start bit, we have a data payload of 8 divided by a header of 2, 1 stop bit, 1 start bit, plus the data, which allows us to compute our utilization as only 80%. Turns out we would like to have extraordinarily low utilization if we want improved performance. I'll give you an example. If you're on I-95, you don't want anybody else on it. You'd like the whole road to yourself, which means the road is underutilized, but you get great performance because you can get to work quickly. On the other hand, if the road is extraordinarily well utilized, perhaps next to 100%, performance has declined dramatically, you're stuck in traffic and it's bumper to bumper. So utilization has a performance that varies inversely with respect to its non-dimensional number, right? So this number has no dimension associated with it. It ranges from 0 to 1. Other examples of utilization and performance, consider the helicopter. Right? The helicopter could weigh, I'll make up a number, 5,000 pounds. And the person who's flying it weighs perhaps, make up another number, 200 pounds. That's a nice round number. So now we get the utilization as being equal to the payload, 200 pounds, divided by the overhead of the helicopter, 5,000 pounds, plus 200. So this is an extraordinarily high performance device, but it is strongly low utilization. Whereas if you had sneakers, maybe the overhead of sneakers is only 1 pound. So you could have very high utilization there, but your performance is rather poor because you can't fly up in the air like a helicopter. So that's a good example. You could do it with Saturn V missile, right? This is something that weighs many tens of thousands of pounds, and there's only 3 people on it. But that can go to the moon. But the utilization is extremely low, but the performance is very good. So now we've got this idea that we've got to address each node on the bus. We get 10 bits. On the Arduino, we get 7, but it says up to 10 bits. So that means I can have 1,024 different devices on my bus. I don't know how to put 1,024 different devices on an 8-bit toaster controller, but in any case, it's nice to know that you can, or at least in theory. I've never seen anything quite like that, or even 7, which would be 128 devices. I would think that's a lot. Pretty sure if you have a budget for 128 devices, you could probably get yourself an extra 8-bit toaster controller and break it up a little bit. But anyway, there it is. There's a protocol for communication. With the address extension, you can get your grand total of 10 bits. There's 8 down in here, and looks like there's another 4 over there. So isn't that 12? Just a minute here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, it looks like 11 to me. I think there may be an error there. So then this is what I'm used to dealing with, just a 7-bit slave address. And I don't envision needing more than 128 devices on my Arduino anytime soon. But that's just me. You guys might want to do that. I don't know. Let's see, what else can we say here? Slaves can be receivers, or they can be transmitters, and masters can be transmitters or receivers. So you can talk in both directions, just not at the same time. And you want to have some kind of an acknowledgement, and that acknowledgement will allow you to have a reliable means of communication so that you can transmit a code word, and if it comes out with a bad checksum, you can issue a negative acknowledgement. And so that's important, being able to acknowledge what you've received. So whenever I am transmitting data from one microcontroller to another, oftentimes I will do it without any form of error checking or acknowledgement, just because I'm a wild and crazy guy and I'm trying to make a simple first example. But that's not the way to do it if you want to have reliable digital data communications. You really do want that acknowledgement. And when you don't get it, after a timeout, you do a retransmission. So the negative acknowledgement, that tells the receiver something went wrong. The checksum's no good. So a negative acknowledgement is an affirmative way to get the transmitter to retransmit. If you never received the data to begin with, no acknowledgement comes back, and then what happens is the transmitter retransmits because it times out. It waits a certain amount of time, the acknowledgement didn't come, so it retransmits again. This is probably too much information by half. Let me see what we can do to start looking at some of the homework questions. All right, so we've seen some multicast questions already. What do you think? Is that a multicast address? This appears in, I'm looking at question 1 in homework 10 right now. Going to call on Shamrock. What do you think, Shamrock? Are you there? Moving to Ricky.
I'd say yes.
Yes, that's true. That is a multicast address. Here is a multicast address being converted into a name. You get that internet address instance, and if it is not a multicast address, then it says it's not, and it'll tell you. So that can be the get multicast address method, can help you. So to get a multicast socket, you need an address and a port just like a unicast socket. Does that sound true? Let's see who else we can talk to. How about Rakibul? Did I pronounce your name correctly? Rakibul?
I'm here.
Yeah. Did I pronounce your name correctly?
Yeah, that was right.
Oh, good. And what do you think about this question? To get a multicast socket, you need an address and a port, just like a unicast socket. So here it says multicast socket, and there's a port coming in. What do you think about that one?
I'd say true.
So that does sound like it's a correct answer as well. Let me sort of go through some of these and see if there's any questions. What I'll do is I'll just kind of scan through it, and if you guys have any questions, you guys can stop me or pipe in. And I think we've had a little bit of an overlap between this homework and the last one, so that's why I'm sort of hesitant to go through this in detail. Let's see, we've got the time to live. You guys know what time to live does for a multicast socket? Anybody have any questions about that? No questions. Here's a port 1234. That should say int over there, and looks like he's going to make a multicast socket, and looks like he joined some internet address. And what was the question? In the following code, datagrams are sent through a multicast socket. So that's sort of there's a datagram, and it looks like it's being sent. So that sort of looks true. Any questions about that? When you get into the network programming class, if you go and take it, we'll get deeper into this stuff, and you'll be able to actually try some of this network programming. So that was question 6. And the next one is a true-false question. Consider the following code. String read job implements runnable. What's this do? Runnable. Implements runnable. I think I'll call on somebody again. Nicholas, what does this runnable thing do? What's that about? Implements runnable.
I don't really know, but I feel like it's implementing like a different class from somewhere else.
So yeah, you're close. It's implementing an interface called runnable. And the interface specification requires that you have a method called run, which is over in here. And what you do is you take an instance of the string read job and you pass it into a thread. And that thread will proceed to, when started, be ready to run. And once it is allocated CPU time, it runs this method. So somewhere in here, the socket, the group, and the port are all provided as local objects, private objects. And then this thing is getting a buffer, and it proceeds to make an instance of a datagram, and he does a socket receive, and so the datagram comes in. So now he's received the datagram. He's the receiver of a multicast datagram. And then he proceeds to make an instance of a message out of it, taking the datagram, converting it to a string, and then he prints out the message. So he gets some data, and he prints the data. And so the job of the string read is to read in a datagram and print it. And that is all it does. It runs by reading in datagrams and printing them. So that is true. So here's one that's that should be familiar to you. I think we did something with serializable last time. It says it's transient, and that's question 8 now. And we would expect the entire class to be serialized. Does that sound right? Let's see. I'll call on somebody. How about Lamb? What do you think, Lamb? Does that sound right? Will the entire class be serialized? It's implemented serializable. So you think yes? Yes.
I don't think so.
No, that's right. It will not. And the reason why is because of this right here, transient. Because it's transient, the name will not be serialized, but everything else will be. So we have prevented the name from being saved.
Professor?
Yes, sir.
Could you just quickly clarify the transient keyword does what?
The transient keyword tells the serializable object not to serialize the instance of the string class. So when you have something you do not want to save, like a social security number, or perhaps a reference to some other much larger data structure that would simply recursively save this and the thing that it points to, because they could be pointing to one another, then you declare it as transient, and it prevents that data structure from being saved out. So I could have student data, maybe he's got a reference to the payroll because he's also a work study student, but I don't want to save the payroll. I just want to save the student's data. So I declare the payroll as transient, even though he may be on the payroll. And that reference to the payroll will not be followed, and the entire payroll won't follow the student when we go to save the instance of the student. Besides which, that payroll could point to a bunch of other students, and those students may, in fact, because they're on the payroll, they have their own private sort of properties, and some of those might include a pointer back to payroll because they're on the payroll. So it might be very good to have payroll be declared as transient, even though we'd like to know which payroll they're on. Maybe they're on a grant, maybe they're on a teaching assistantship, I don't know. And we don't want serialization of the entire payroll system if all we wanted was to save a student, because that wouldn't make sense. If we wanted to save the payroll, we'd go save the payroll. So here's one called test write, and we make an instance of the student, and we set the name J. Schmo, but we already know that the name is transient. We know it's transient. The grade, that'll be saved. And then when we go to print the student data over here, SD, we would expect that it would print out in some nice string method, but we don't know what the toString method is in student data because we hadn't seen it. So now we take the whole output stream. We write an object out to it. File output stream is put in as an argument to the object output stream constructor. And then we take this instance, and because it implements serializable, the object output stream converts it into a sequence of bytes, a formatted stream of bytes, in fact. And then we close the object output stream, and then we're done. Now later we can go open the file, run it into an object input stream, do a read object, and reconstitute the student data with everything except for the name, because the name was held as transient. Then it says here, The above code will write out an instance to a file. That sounds right. It says it is impossible to write an array of bytes. Does that sound true? Can I just write this out to an array of bytes? How would I do that? This thing wants to do a write object. He needs an output stream. How would I write this to an output stream if I want to write it to an array of bytes? Let's see who else has. Jorge. And I guess that's how you pronounce Jorge. Is it Jorge? I'm just gonna. Yes. Did I get you?
Yes. One second. I have another sound coming in. Okay. What was that?
Yeah. So it says here that the above code will write out the instance to a file. It is impossible to write to an array of bytes. Does that sound true?
Above code is impossible. To an array of bytes, instance to a file. That's true, right?
No, that actually is false. Sounds like you've got a little sound going on in the background. So
Yeah, I'm home. So
it's all right. Yeah, I am too. It's okay. So what happens here is if you are faced with an API that will only write to an object output stream, you don't have to use a file output stream as the argument. You can use any output stream as the argument. And so then when you do the writing of an object, it will go to the output stream. And so what you can do is you can use a so-called byte array output stream. So not to put too fine a point on it, let me see if I can find a browser window here. And I will show you the byte array. Oh, there it is. Pops right up. Byte array output stream. So it's actually been around for a long time. You can essentially make an instance of the byte array output stream, and it extends the output stream class. And they've had it since JDK 1.0, so this has been around for a very long time. And so then you can just call it, something like BAOS, byte array output stream, and you can pass that in with the same argument you would normally do a new output stream. Instead of FOS, file output stream, you put in BAOS, byte array output stream, to the object output stream. And then when you write the object, it goes to the byte array. And then you could do what you want with it. You can broadcast it on the radio. If you have a little radio, a transceiver or something like this. So you don't have to write it to a file, that's for sure. You could send it down the serial port. Serializing down the serial port. Doesn't get better than that. So here it is. Oh, wow. Look at that. A byte array output stream. And it's been pre-allocated with 512 bytes. And now we're going to serialize the object to the byte array output stream. And then it says here, we convert the byte array output stream to a byte array. And it returns as an array of bytes, which is so cool. And then it says here, the above code will take any object and convert it into bytes. Well, any object? No, it sounds like any serializable object, maybe, but not just any object. All right. So what would that be? It's got to be a serializable object. So that's false. So let's have serialization is so important because if you're going to try and do distributed computing, you're going to have to take instances and pass them across the network. And then the question becomes, well, how do I do that? And the answer is through serialization. So not only are you going to take the byte array output streams and not write them to a file, you're going to write them to an output stream that may be associated with a socket, which means it will be connected to another machine, not yours, somewhere else on the network. That's a rather important thing, because if you're going to try and do distributed computing, it's real important for you to be able to take instances and transport them across the network. So here's an instance of a string, right? Hello, serialization world. And here we've allocated 512 bytes of data. And now we take the byte array output stream and make an object output stream out of it. And then we go to the object output stream and we write, hello, serialization world. Now we can take the new byte array input stream from the bytes that we just created, right? And now we can read them back in. Reading them back in means read object. And what comes back from that array of bytes? Well, here comes my string. So not only can the serialization do a persistence of the object by saving it to a file, it can transport the object from one data type into another, where the one data type it transports into is the most general of data types, an array of bytes. And then that can be saved anywhere or sent anywhere. And not exactly sure why this auxiliary variable was created. I think I could have just inlined the obj right here, but it doesn't matter. What was the question? The following code makes a clone of the object. So now, here's the interesting thing. Is obj equal to s? Equal. Well, it depends. If equals is s dot equals obj, then the answer is yes, because they both contain the same string. But if equals is equal obj, then the answer is no, because these are different references. We've made a copy of the instance. In a sense, we've cloned the instance. All the things that are important about the instance have been copied, but the instances themselves are separate. Strings are usually held as immutable. So if you want to make a new string, you basically have to make a copy. So this is a clone. Right? The following code makes a clone of the object. They are equal in the equals sense, but they are not equal in the equals sense. They are two different objects, and they have been cloned with respect to one another. So that's one way in which you can copy two objects.
Professor?
Yes, sir.
Why would you want a clone of an object and not just to reuse the same object?
Well, if you wanted to do something to the object surgically, you might like to leave the original object alone, make a clone, do the modification, and then use it however you like, and then perhaps dispose of it horribly in flames. Throw it into the garbage collector, then get shredded. I'm thinking the garbage collector is kind of like this pathological narcissist that just loves to chew on memory and return it to the heap, but it's probably just a program that doesn't know what it's doing. Yeah, so right, making copies of objects is a reasonable thing to want to do. Lots of reasons you might like to copy an object. For example, suppose you wanted to do something like A equals B plus A. If you reuse the object, you've made, kind of a problem because now A is gone. The original A is missing. So you might like to make a copy of A to hold it someplace and then do the modification and see if the two things are equals, or equals. And if you said, well, A is an image and B is an image, and I'd like to know if A and B are comparable or something like this, I can make a comparison image. So I could say compare A and B. Makes a new image. If it destroys A in the process, that might not be good, especially if I wanted to have that image later, the original image. So lots of reasons to make a clone. I can think of no more, but I think there are probably more. We could ask. Actually, I learned so much when people ask me these questions. Why do I make a clone of an object? Make an exact copy. There's new instance, the clone, but why? There is no operator to create a copy of an object, but we already know that we can do it if we have serialization. And why do I want to make copies? I don't know. I can't think of a good reason. The more I thought about it, the more I said, oh, the clones are useful in some kind of computation. The advantage of object cloning. Some design issues, a popular, easy way to copy objects. You don't need to write lengthy and repetitive codes, just an abstract class with a clone. Just to find a parent. Disadvantage of cloning. There's lots of disadvantages. I don't see the good application example here, but I think with enough Googling we could find it, but I'm not going to spend too much time looking. You're really cloning the object when you send it across the network. How's that? Because you have to serialize the object in order to transmit the object. So you're basically making a data encoded copy of the object for the purpose of saving to a file or transmitting across the network. In fact, if you were going to transmit it across the network and then have it come back to you identically, you might like to compare it against the original. So that essentially you've transmitted the clone. You get the clone back and you can compare it against the original and see what happened. That's all I got. There may be better reasons. So let's see. We're not getting any packets back from the local host. Does the following fix the problem? So we said set loopback mode, disable false. Does that fix the problem? Set loopback mode, disable false. You guys might not know this, but the answer is yes. Yes, indeed, that does fix the problem. And here comes some questions about the inter-IC bus. The integrated stands for integrated circuit. Integrated circuit. So that is true. I2c bus. Let's see. In I2c bus, only one bus is required for communication. Bus is required. The serial data bus. One bus is required. I think this should say one wire. One bus is required. Yeah, that should say one wire. Let's modify that. I just noticed this small error here. That should say only one wire is required for communication. The serial data wire. Here, I fixed it. We'll see that next time. Let's see. Now, is that true or false? In I2c, only one wire is required for the communication, the serial data wire, SDA. We just had the lecture on this. So let's see. I'll call on someone. Looks like John Fee is here. John, what do you think? Is that true or false?
If it's one wire, then it's false.
Yeah, that's false. You need two wires. You need the data line and you need the clock line. It is a synchronous half duplex network bus, or bus network if you like. Let's see, here's one. I2c is half duplex. I think I already gave that one away. That's true. That is half duplex. Let me see where we are here. This is question number 16. I'm just checking to make sure my answer key is correct because these are new questions. So then here comes question 17. In I2c, master sends the start bit. So we've seen the timing diagrams on that. And so we know that it does. It has a start bit, it has a stop bit, and these are what they call framing bits. So framing bits essentially frame the data during its transmission and reception. So yeah, computer architecture. Isn't that fun? You get involved in buses now. It isn't possible to have multiple masters in the I2c bus. It isn't possible. This is question 18. Let's see if we can find somebody. Jacob, what do you think about question 18? Is that true or false? No, you can support multiple master and multiple slaves. You just have to take turns. So that a statement is false. You can have them. You can have them. Let's try question 19. Data must be stable when the clock is high for a correct I2c bust transaction. So that's a timing diagram question. Let's see who hasn't gone yet. Daphne, what do you think of that one?
True.
Yeah, that is true. That is true. Let's see, question 20. Hot swapping. What does that mean? What's hot swapping? Anybody know what that is? Hot swapping. Hot swapping, that's when you take something that's live, you unplug it and plug it in. So that's kind of like plugging in a lamp while it's on and the light comes on right away. If you got a bus and it's active and then you just slap on something while the whole thing is running, that's a hot swap. A hot swap to the bus is something you're not supposed to do with certain kinds of buses because it's considered electrically unwise. And so it can cause power surges and drops in current and things like this. So that's not something we've covered before, but the answer is yes, you can hot swap. So this bus is very robust in that sense. You can just plug stuff in and unplug it while everything else is running and communicating. It might cause a glitch, and maybe somebody will have to retransmit, but it is considered okay to do that with the I2c bus. So then comes the next one, which is quite related to hot swapping. Devices can be added and removed while the system is running in the I2c. And let's see, we'll try Caroline. Caroline.
That's true.
Also true, right? Because if you can do hot swapping, then this must also be true. And so then here comes question 22. He says I2c protocol is connected with serial RAM, LCD, double EEPROM, and is used with television sets. Television sets. Huh. Could that be true? Let's find somebody else who hasn't gone. Alexander, what do you think? Does that sound true?
That would be true.
Yes, that
Yep.
is true. It's all over the place. Serial RAM, double EEPROM, LCD displays. It's even inside your car, probably, or television sets. So we've got. I mean, you can find it with relative ease if you grab a Google page and you just say you want some. I want I2c RAM. There it is. There's some I2c RAM, and it's cheap. And in fact, it comes with a little module, which isn't that expensive either. And you can just slap it on your little microcontroller and you can talk on the I2c bus. So when you're doing computer architecture and you say, you know, what I really need is a place to store my memory, and you say, oh, I want some I2c double EEPROM. Oh, there it is, 44 cents. And, you know, from an architecture point of view, slapping on some double EEPROM is good because that may be where you store your program, right? Microcontrollers like to sort of have their program handy just as soon as they are turned on because they don't have an operating system where they can boot from, like, I don't know, a hard drive or something similar, flash drive. Instead, they want everything to be in memory right away. Double EEPROM will let me do that. Suppose I want I2c DAC, digital to analog converter. Oh, there's one. Microchip has one here. There's a DAC from somebody else, and I got a little module. It's not terribly expensive. I can get one. And that's unit quantity too. I mean, you know, you're going to get a break in the price when you order your first 10,000 or something. And if I want, I can get an ADC, the analog to digital converter, slap it on my Raspberry Pi. Here it is for 96 cents. And there's a PC board for under $5. Cheap. And if you want I2c for, I don't know, a real-time clock. There it is, real-time clock. I have a bunch of these. We do this in the lab. Those of you who are in the embedded controllers lab have already seen this one. And if you want I2c for LCD, yeah, LCD display. That sounds like a good thing. There they are. Ooh, $249. What is that? They're nuts. No, here it is, $250 for $2.50 on eBay. I don't understand that. LCD quote for $249. That doesn't make any sense. I don't know what that is. Maybe it's made out of polonium or something. So there's a, you know, there's a little lab we do in the microcontrollers where we use the I2c bus and make a little LCD display. And so you can just slap all these things together and they all have their own address and they can all talk to your little microcontroller. And so what have we done? We've done the A to D converter, D to A converter, real-time clock, LCD display. How about some other I2c thing? I don't know. Let's think of something we might need in a computer. I'm running out of ideas. An I2c list. Is there a list? Oh, I know. How about a temperature? Temperature sensor, sure. Humidity sensor, why not? You want sensors? We got sensors. Temperature and humidity sensors. There it is. And we've got these in the lab, and they're very inexpensive. So you can get all kinds of I2c sensors. I wonder if you can get something for the wind. I don't know how that would work. Yes, they have that. Look at that. I've never had this. An I2c wind sensor. How cool is that? And there's a level sensor. And I guess maybe if you wanted to measure a fluid, you'd want a level sensor. Right? I2c level sensor. There's tons and tons of, here's water level sensor with analog to digital converter. I2c. Convenient interface. $25. Oh my God. It's offended my sense of thrift. Look out. There's probably, oh no, that's expensive too. Well, aside from the fact that they're expensive, they are there. So what about an I2c radiation sensor? I never bought one of those before. Here's a Geiger counter. Ooh. So this is more I2c interface stuff than I've ever seen. I never had a gamma radiation sensor module. And you know why, right? Because if you have gamma radiation in the lab, people won't like it. I wouldn't like it. So yeah, we don't need that sensor. I don't want gamma radiation in my lab. That doesn't sound like a good idea. So yeah, you can get I2c sensors for just about everything, I suppose. But there are limits, right? They don't go as fast as other kinds of protocols, but 3 megabits per second, that's fast enough for most applications, or for a lot of applications, let's say. Let's see, the advantage of I2c is its synchronous communication protocol, so there's no need for a precise oscillator for the master and the slave. Let's see, who hasn't gone yet? I think I called on everybody. Yeah, I did. Go back to the doing this myself. So yeah, that is true. I only need one clock. If I have a slave and I've got a master, the master can have the clock. If I've got a microcontroller, it's already got an oscillator, so I can divide that down and use that as the bus, and then the bus can be distributed to all the slaves. So I really only need one clock for the whole system. The slave doesn't need it. It can use the same clock to respond. So that's fine. And this looks like the final question in my little list. Half duplex communication means data is transmitted in both directions. What do you think of that, Stephanie? We're back to the bottom of the list. I started at the bottom, so I'm back to you.
I think that's true.
So if you have half duplex communication, data is transmitted
that's false.
only in
Sorry.
one direction because, of the single data bus at a time. So you need full duplex to have data transmitted in both directions at the same time. So an example of a full duplex network might be a serial peripheral interface, or RS-232. Those are both, full duplex because they have transmit lines, TX, and receive lines, RX, and they can both be used at the same time. With SPI, it's master out, slave in, master in, slave out. So they have, a transmit and receive line for SPI, or serial peripheral interface. So that's another synchronous bus, but that's a full duplex and much higher performance bus that requires 4 wires instead of 2. So this is a 2-wire bus. And that is what I have for you for today. You've got, how many more of these I2c slides to go through? Oh my God, another 20? It's the PowerPoint death march. I don't think we need that. So it gives you kind of a little overview of the I2c bus. From a computer architecture point of view, it gives you an enormous amount of flexibility with a very low cost bus that's relatively low performance, but you can kind of see why there's a market for that. You're dealing with chips that all cost less than $1. You're dealing with, the Internet of Things, which basically means interfacing everything to everything else, which is kind of a tall order. And in order to do that, you want a substrate that allows hardware component development. And that means you want to be able to have a bus that everything can plug into and talk to each other on. And so having a convenient, low cost, relatively low performance bus is a great way in which you can architect computer-based systems. So from a computer architecture point of view, it's plug and play with a whole bunch of different things that you can buy inexpensively on places like eBay. And then you can create the system that does what you want, whatever that may be. So that's what I have for you for today. Stay safe, and thank you for your attention.
Thank you, Professor.
Thank you.